Friday. Happy midterm day, more specifically, I guess. Your midterm scores should have been sent out. I submitted them before the deadline this morning. And that said, at this school, midterm grades are just kind of a vague letter grade. And weirdly, the better you do, the vaguer the letter is. Because C through A all translate as S for satisfactory. Anyway, the point I'm trying to get to is, if you want to know your actual midterm score, like a number, ask me and I will gladly tell you. That is not secret information. I just have yet to build a system where you can view it without asking me first. I'm actually working on that though. I'm going to try to get the Brightspace grade system set up so that you can see your current average as of the midterm. As a reminder though, that midterm score includes, it's your current average, so it includes test 1, your lab average up till now, and your homework and quiz averages up through chapter 5. So if you haven't been doing the homeworks and quizzes, that would lower your midterm score, and then once you do them, as long as you do them by the end of the course, that'll rise. Again, any questions about the score, please let me know. Separately, if you didn't pick up your test on Wednesday, I have all of those together here in a pile. They are yours to collect, they are yours to keep, so do please come grab them, because if you don't grab it to study from, it's just going to take up dust in my filing cabinet. And it would far benefit the universe if you got some use out of it using it to study for the final. Now, main objective for today is we're going to be starting chapter 6. We're moving into the latter half of the course. Chapter 6 is going to be about momentum and collisions. And starting next week, we'll be back on our usual schedule of chapter per week, lab per week, until about Thanksgiving. So, any questions from you guys about anything before we get started today? All right. I left the word momentum at the title slide, and there we go. So, once again, chapter 6 will be about momentum and collisions. We have kind of very briefly implied a few things about collisions. And momentum is actually one of those physics words that does exist in the English vernacular. So I'm hoping that these concepts are not foreign, like entirely foreign to anyone. In a second, we're going to define collisions and then define momentum. First though, I kind of want to just ask to gauge your feelings on the to gauge your knowledge on the subject. When you hear the word momentum, based on how it's just used occasionally in common English, what comes up? What possible definitions come to mind? What sorts of places do you hear the word momentum used occasionally?
Driving.
Driving? What about driving?
Like in driving school, like to keep a safe distance from like a bigger truck because they'll come at you fast or like behind you faster or something, or they take longer to stop.
There we go. Perfect. Bigger truck moving quickly takes longer to stop. That is actually a perfect use of the term momentum. Because momentum is, to define it scientifically, a measurement of how difficult an object is to stop. More on that in a minute. First, I want to define collisions. Now, I assume you know what a collision is, basically. But we do need to define things in terms of the physics we're going to be using. So the physics definition of collision we're going to be working from is an interaction between two or more objects that come into direct physical contact with one another, and over a period of time, the objects involved in the collision exert forces upon one another. And during this time, because of these forces, the objects tend to swap and trade both kinetic energy with each other, but also momentum with each other. And that's kind of why we're going to be talking about momentum and collisions in this chapter. It's not really two halves to the chapter, it's two current themes all the way through. couple points from the beginning half of this slide I'd like to address. Oh no, my earlier notes are gone. Bless you. Within a collision, two objects are going to physically collide with one another. And one of the hallmarks of collisions is that two objects are going to exert forces upon one another. If you have ever run face first into something, you are aware of this. Force, not only is the force going to be exerted on both objects due to Newton's third law, whenever A acts on B, B will act on A, and that's why, again, if you run into a door, the door is gonna hopefully open, but your nose is also going to hurt because forces go both ways. Anyway, those forces are going to cause the mass of either object to accelerate, and acceleration changes velocity over time. So, things I want to take away from this are, the force involved in a collision causes the velocity of the two objects involved to change, and this process takes place over a certain finite amount of time. It's not instantaneous, it's not instantly the speed is different, it takes time. Like it takes time to hit the brakes and slow down. It doesn't always take a lot of time. For example, fair warning, if you are looking at your computer or your paper, I'm about to drop a golf ball and it's going to make a noise. So, noise ahead. How long did it take the ball to actually collide with the desk? Like from start of contact to end of contact. It's like the blink of an eye, right? Too fast to process. Human brain might not be able to catch it, but it does still take a certain number of seconds. Maybe like a millisecond, but that's still a number. It's not instant, it does happen over time. It's a very small amount of time. And over that very small amount of time, the speed of the golf ball is going to change. It goes from pretty quick down to less quick up, which is actually a pretty big change. It changes direction completely. So that's a pretty big change in velocity over a very small amount of time. Is that going to create a very large or very small acceleration? Large. If you take a big change in velocity and divide it by a teeny tiny time, like less than a second, you're going to get a big acceleration. Dividing by numbers less than 1 gives you a bigger answer. And a big acceleration is caused by a big force. This is again why collisions hurt. And the more force involved, the bigger the change in velocity and the more pain. But there's a change in speed, and it happens over a finite amount of time, even if that amount of time is too fast for a human to catch without technological assistance. Because of that change in speed, and note that both objects are going to change speed, technically, that change in speed is why, or it's the proof, that the object is going to be changing both its kinetic energy level and also its momentum level. Because velocity determines both of those things. If you remember the formula for kinetic energy, 1/2 mv squared. If you have less velocity, you have less kinetic energy. So if the velocity of the ball changes, its kinetic energy level changes. And that is why collisions change the kinetic energy level of objects. As long as the speed changed, the kinetic energy changed. And the same will ultimately be true for momentum as well in a second. So, collisions, forces act on both objects for a certain amount of time. That causes them to accelerate. That causes their kinetic energy levels to change. And I can prove this because I'm going to drop the ball again. Note the height that I'd start dropping it from, and I'm going to catch it when it rises back up. It didn't rise to the same height. And this proves some of the kinetic energy it initially had on impact is gone. Not only did it transform, it went somewhere else. well, it transformed and went somewhere else, both simultaneously. The force involved in the collision does work on the golf ball and causes its energy not only to change states, but also to go somewhere. And the fact that it doesn't rise to the same height repeatedly, so repeated impacts ahead, is proof that every single time it hits the ground, it's losing more and more of that energy. It doesn't, like on impact, some of the kinetic energy goes away, and therefore it's not all there to turn back into GPE, therefore it never rises quite back to the same height. Even the best turbo bouncy ball you can get out of a, I don't know, Kmart dispenser at the door. I'm not the only kid that got those once or twice, right? Even the best one of those will never quite rise up back to the same height because of that fact. On impact, you'll always lose some energy. And that loss is because energy can turn into lots of different forms. It turns into heat in the ground because pretty much all forms of friction and negative work are going to turn some energy into heat. But also, some of it turns into sound, interestingly, because, and this is why I like to lecture about sound at the end of the semester as well, sound is just moving air. And air is made of matter. It's not a lot of matter, but it is matter. And so if sound is moving air, to hear something, something had to make the air move. And that means that the matter of the air needed kinetic energy in order to move. So if you heard something, that means that whatever made the noise lost energy to the air for the sound to have happened. So the fact that you hear this, impact ahead, is proof that the ball didn't have, like, lost some of its energy, because now some of it's in your eardrum. Usually the quieter something is, the more energy it maintains on impact, which is another reason why those turbo bouncy balls are usually pretty good. They're just quieter on impact. They lose less energy to sound. All this to say, kinetic energy in a collision is sometimes hard to track because it turns into lots of different forms and escapes all over the place. And that's why we're going to start talking about momentum. Because momentum doesn't do that. Kinetic energy turns into lots of different states and goes everywhere. But momentum only has one state. Momentum. Questions on this slide before I go on to define momentum? Or anything that I've said for the past 5-10 minutes? All right, so defining more terms. The definition of momentum, that's the second line after the formula. Momentum can be thought of as a measurement of how difficult an object is to stop. The more momentum something has, the harder it will be to bring it to a complete stop. The less momentum something has, the easier it will be to stop. If something has no momentum, it's quite simple to stop because it's already stopped. If you have no momentum, you aren't moving, therefore you're stopped. Let us now look back up at the formula for momentum. The formula says rho equals mass times velocity. Frustratingly, the m in that formula isn't momentum, the m is mass. But m has always been mass, so that's actually consistent. The weird thing is that the physicists ran out of English letters a long time ago, so we had to start stealing from the Greeks. So this, the symbol for momentum, is officially lowercase Greek letter rho. There's not a fraternity or sorority on campus with a rho in it, but that's a rho, and that's how it's spelled as an English word. It is technically distinct from a lowercase English letter p, because most lowercase English letter p's have this little thing on them, even if it's very subtle. But rho is just smooth all the way around. It's kind of like you took that music symbol and just rotated it 180 degrees. And it's further differentiated from uppercase English P because it's lowercase. and small. I'm really only pointing this out because I think of it as rho, so I'm gonna say rho equals mv. And I wanna make sure that that makes sense. When I say rho, I mean momentum. I mean, that simple. Sound good so far? All right. This is the point of the course where the variables, like which variables exist for what concept, are gonna maybe get a little frustrating, because like I said a second ago, European physicists ran out of English letters to use a long time ago. We didn't use m for momentum because it was already being used up for mass, so we needed something else. I don't have a good reason why they picked rho. Maybe someone called it rho-mentum at some point. There's also a dumb story about, a very fake story about Newton explaining it using the example of a pimento inside of an olive, and he called it pimentum, which starts with a P, but that's dumb because it's rho. It's a very dumb story. Whatever the reason, it's rho. You can call it rho-mentum if you want to. And the letters in the formulas are just going to get weirder. We're going to start stealing more from the Greeks. Kind of surprised we didn't start stealing Cyrillic letters at this point. So, rho equals m times v. This means that the more mass something has, the harder it is to stop. And the faster something is moving, the harder it is to stop. You know this if you've driven on the highway, because if you're moving at 80 miles per hour, and then you crest over a hill and suddenly see 3 miles of traffic ahead of you, it's quite a pain in the butt to slam on the brakes and come to a full stop out of nowhere, correct? Vehicle moving at interstate speeds is pretty hard to stop because it's moving very fast. But additionally, the bigger the car you're driving, the even harder it is to stop, which you know if you've driven a truck at interstate speeds. Something else I'll point out about the formula, because velocity is a vector, and because nothing weird is happening to it, like squaring it or something, momentum is also a vector, and it inherits the direction of the velocity. What this means is that momentum not only tells you how hard something is to stop, it also reminds you what direction it wants to be moving in. If something is moving east very quickly, it wants to keep moving east very quickly. Even if you put a brick wall in front of it, it's going to slam through the brick wall and keep moving east, right? So it's not only very hard to stop moving objects, it's also even harder to turn them around. So momentum's a vector, variable is rho, inherits the direction of the velocity, and last thing, since it's a new variable, it has its own unit, and frustratingly, it does not have a designated specialized unit. The unit for momentum is kilograms times meters per second in its entirety. It is a mouthful. And we never gave it its own customized unit because no scientist put their name on it, I guess. The real problem is that most of Europe's work on momentum came from Newton, interestingly, and we already put his name on the force unit. I don't know why they didn't just call it an Isaac, because there's 2 parts to his name, but we're stuck with kilogram meters per second, unfortunately. But if you ever have a hard time remembering that unit, I'll just point out, it's just comprised of the 2 things that went into finding it. Kilograms times meters per second. You are still allowed to think of it as a pain to say out loud. Imagine me having to say it 80 times a day. Questions on the definition of momentum thus far? All right. New formula, therefore, very quick sample math. Here we have 4 different scenarios. 3 of them feature inanimate objects, 1 of them features an organism, all moving at different speeds. Very quickly, please tell me which of these 4 scenarios has the most momentum in it. See a lot of votes for B, and B makes sense. Just given that very fast speed. I'm gonna roll the board up and reveal the answers. The winner, just in terms of the most momentum, is actually C, the dog. Why isn't it A? It's not moving. No matter how big the mass of something is, if its velocity is 0, its momentum is 0. So this building is very easy to stop. It's already stopped. If the building was moving, we'd have a lot of very different problems. The bullet is a reasonable guess because of that very big velocity. However, its mass is teeny tiny, 10 grams. And the unit for momentum is kilograms, meters per second, so we do have to convert that first. 10 grams, if you drag the decimal point 3 places to the left, is 0.01 times 1,000. Is only 10 kilogram meters per second. So high speed, does matter, but when paired with a tiny mass, it just doesn't necessarily translate to a lot of momentum. I'm skipping C for a minute. D is kind of the opposite scenario to B. We have a very massive object moving very slowly. Note that this is 1 centimeter per second, so that has to be converted into meters per second before using it. There's 100 centimeters in a meter, therefore 1 centimeter is 0.01 meters. So that's only 2,000 times 0.01, 20 kilogram meters per second. This car is surprisingly easy to stop because of how slow it's going. All you really have to do is just put your foot on the bumper. That leaves the dog. Its mass and its velocity are already in the correct units, so 25 times 10 is 250. If you've ever watched footage of dogs being trained to do things like stop intruders, a dog going full tilt at one of those guys in one of those suits, like the big ones that you see in the dog training videos, dog barreling full speed at a person, jumping right at torso, person's hitting the ground. Dogs are cannonballs. I know this because my puppy, she's not a puppy actually, she's 2, 40 pounds, very low to the ground. If she is running straight at me and torpedoes straight into my leg, I'm not going to be standing up afterwards. So technically, just in terms of amount of momentum, the dog actually is the winner here. Questions?
What kind of dog do you have?
I have 2. The aforementioned not puppy is a boxer pit mix. Weirdly long, like very low to the ground and very long. We call her Penny. And she is just a goober. She is a floppy-eared goblin that all oscillates between napping and full tilt, must play, must devour everything. The other dog is Lucy, who is most likely a pit Basenji mix, and all she really wants to do is just sleep in the sunlight next to one of her people. So the 2 of them don't get along because they want very different things out of life.
That's cute.
Any other questions for right now? All right. So, how are we going to use momentum in this? Skipped a slide there. How are we going to use momentum in this class? We're mostly going to be thinking about it. I will occasionally ask you, on a homework question, what is the momentum of this object? But we're also going to be using it in the context of collisions. And we've already done math similar to this because a collision is really a before and after state. You always have a state before impact, and then you have the state after the collision has completed. So using the crash test car dummy example that I bring up a lot. Watch old episodes of Mythbusters, by the way. Before collision would be the moment before a remote control car hits the wall. Car is moving at speed, wall is not moving. And then after collision, after everything is done, the car has come to a complete stop, its front end is now pancaked, and the brick wall has flown off in various directions. So, a distinct before versus a distinct after. And we've already done examples similar to that, because we've done cases where we looked at the energy in a process, in a scenario, both before some process transforms the work versus after some process transforms before the energy is transformed versus after the energy is transformed. So examples like we did where we looked at the KE versus GPE of a rising or falling object. Those have a before and after, where we looked at the energy totals before and after. And you can do the same thing with momentum. In fact, it's arguably more straightforward to do with momentum than energy, because energy has lots of different forms that you have to keep track of. If I throw this thing up and down, you have to note how much energy is in the gravitational potential or kinetic state at any point in time. Whereas here, momentum only has one form, momentum. There's not like different types of momentum, it's just momentum. I'd say the closest thing to a different type of momentum is just different directions, since it's a vector, but we're really only going to do one-dimensional collisions in here for simplicity's sake. So there's no other type of thing that momentum can be. And similarly, momentum is conserved in a collision like how energy is conserved throughout the universe. If a total amount of energy exists in a system before something happens, the same total amount exists after that process. It's just in different forms and in different places. Momentum is similar. If a system has a certain amount of momentum in it before a process takes place, that will still be true afterwards. But rather than changing forms and changing objects, all momentum does is change objects. It stays momentum. So there's, in my opinion, fewer things to keep track of. You don't have to worry about what type of thing exists, it's just momentum. And so we'll be using it to, for example, determine the velocity of objects after a collision. Questions before we do that? All right, so for our last little bit of practice today, let's cause a collision. We're going to shoot an arrow at a log. This process is going to have a distinct before state and a distinct after state, or initial versus final, that we're going to be comparing to each other. In our initial state, we're going to launch a 10-gram arrow towards a stationary 5-kilogram log. The arrow is going to be launched at 25 meters per second. Within this before state, where is all the momentum? The arrow. The arrow is the only thing moving, so it has all the momentum. The way I think of this, the example is a party, and momentum is the only one bringing food. Sorry, the arrow is the only one bringing food. The arrow brought all the momentum to the party. Now after the impact, the arrow is going to embed itself in the tree trunk, in the log. And what do you think the log's going to do when this happens?
I guess like rock back and forth or fall over.
Yes, it might very slightly recoil. Would you expect it to be knocked back very far, given the mass difference? Yeah, good assessment. But you might expect it to recoil slightly. Maybe if it's on a fence post, it might just barely tip over. Maybe. That's what we're going to find out. But just because of the mass difference, going into this scenario, are you guys expecting a very big final velocity for the log? No, good, we're gonna prove that. Your assumptions are right, we're gonna validate them today. But again, looking at this scenario, I'm actually gonna keep placing down my good markers and getting them mixed up. In this after scenario, we don't quite know the final speed of the log with the arrow stuck in it. We don't know what that is, but all of the momentum that the arrow brought to the party is now going to be shared across the combined arrow log amalgam object. So initially, arrow has all the momentum. As soon as impact is made, the arrow is giving most of its momentum to the log. And we know this because the log might barely move. If the log budges, it is now moving, it must have some momentum, and any momentum it has, it is gaining from the arrow. The arrow brought all the momentum to the party, and now the log is going to eat it. And we're going to prove that mathematically. We're going to trace the momentum through from start to finish. So, we're going to use, first questions before I actually do the math. All right? So, we're going to use, bless you, conservation of momentum, this formula from earlier. It's a lot like conservation of energy, but it's momentum instead. To compare all the initial momentum to all the final momentum. On the initial side, we're going to look at the momentum of the two objects. This is literally just the total of all the momenta of all of the objects present in the beginning. By the way, the plural of momentum is momenta, like the plural of curriculum is curricula. Is that Latin? I don't know. So on this initial side, we need to consider the momentum of each object separately, but added together. So the initial momentum of the arrow, so rho, arrow, I, and the initial momentum of the log, rho, log, I. Now, which of these two objects has all the momentum initially? Yeah, the arrow. The arrow is the one that's moving. We're going to prove the log doesn't have any at the start. But on the after side, the same two objects exist, and so we need to consider on the final side the sum of their final momenta as well. So same two objects, but their final momenta after the collision. Each single object's momentum level is going to change. We know this because their speeds change. The arrow is going to slow down a lot. It's going to go from 25 to stuck. And the log is going to go from 0 to, which is technically an acceleration, even if it's not a big one. Question so far? All right. Remind me, what's the formula for momentum? Mass times velocity. So, to substitute in the formula for each of these pieces, momentum arrow initial is going to be mass arrow times velocity arrow initial plus mass log times velocity log initial. On the final side, we're really just going to replace all the i's with f's. The masses don't change because the object's masses don't usually change. The only real way to change the mass of an object is to break it, and then you have multiple smaller objects. So the masses remain unchanged, but they'll be moving at different final speeds. And something convenient about this specific scenario is that the arrow is going to be stuck within the log. So what does that tell you about their final velocities? They're the same. They are stuck together. They have to be moving at the same final velocity. So thankfully, we don't have two separate final speeds to calculate. We only have one. So I've just written the same VF in both formulas. As long as they're stuck together, they have to have the same final velocity. It's like the pulley questions from a couple weeks ago. The two boxes are tied together, they have to be moving together, which is convenient. It saves us the trouble of having to find two different things. That's why I'm starting with this type of example as opposed to it. No, that's for next week. Questions about this skeleton before we start plugging? All right. Thankfully, we know all the masses, and we know both initial speeds, initial velocities rather. So, 10-gram arrow, how many kilograms is that? 0.01, very good. Times the initial speed of the arrow, which is 25 meters per second, no conversion required. Log, much bigger mass, but no velocity, so its entire initial momentum is just going to go away. On the final side, same two masses, because those aren't changing, but different, unknown, but united final velocities. So thankfully, VF is the only thing we don't know. So we can successfully use this process to determine the final speed of the log-arrow combo act. On the left side, the entire initial log term is just going to vanish, because no matter how big the log is, if it's not moving, it doesn't have any momentum. So that's just going to go away, 5 times 0. This is just going to become 0.25, so I'll just write that as the entire left side. On the right, bless you, we have the same VF in two different places, so I'm just going to use the distributive property. VF times open parentheses, 0.01 plus 5 close parentheses. My F's are weird today. Sorry. And this means, I'm going to finish it out over here because I ran out of board. VF should be equal to 0.25 over 5.01. Any issues seeing how that turns into that? All right. Memory serves, then that is approximately just shy of 0.05 meters per second. Round up to 0.05. Which proves the initial assumption that this log is barely going to budge. You might not even notice that, if I'm being honest. Probably not enough to knock it backwards, like knock it off of a hypothetical fence post. If you want to see the target fall over, pick a smaller log. Questions? Opinions? Concerns? Go good, I hope. All right. Last thing I'm going to do, just very quickly, to kind of prove this point. I'm going to take that final speed and plug it into these two terms on this side, just to prove that the momentum total is the same. 0.25 equals 0.01 times 0.05 plus 5 times 0.05. 0.25 equals, that's going to get really small. So the two sides are about equal. The only error there is just rounding. So the momentum's conserved. All the momentum, basically the arrow had to give up most of its momentum to even get the log to budge. And frankly, most of the math for the next week is going to look pretty similar to this. We're going to be looking at the before versus after state of various collisions, seeing how the momentum transfers from one part of the system to the other, and then eventually we're going to rope kinetic energy back into it to compare how it works to how momentum works. Last thing I just want to say for today is, you can start packing up. Last thing I want to say is, momentum is always conserved even if it doesn't look like it is. For example, noise incoming. I'm going to throw this at the wall. So, now, the collision there was between the golf ball and the wall. The golf ball definitely had a big force sack on it because it turned around. But I guarantee, because this always happens, the ball lost some momentum to the wall. Why didn't the wall move? If the wall had to absorb some of this thing's momentum, why did the wall not ricochet away? Sorry? It did rebound most of the momentum, that is true. The main thing though is just that the wall is massive. The wall is part of the building, and frankly, that wall is just, like, we're underground right now. So that wall is currently backed up by dirt and rocks. So that wall and the earth that it is functionally attached to is massive. So I guarantee the wall gained some momentum, but that teeny amount of momentum shared across the entire mass of the wall or the building or the planet doesn't make it move all that much. This is why dropping an anvil on the ground and therefore sending a lot of momentum straight into the planet doesn't cause the planet to start moving, at least not noticeably, because the mass of the Earth has like 30 zeros. It's that many kilograms. So it gains momentum, but it would have a teeny tiny velocity as a result. And this is thankfully why meteor impacts don't usually knock us out of orbit very often. It would take a colossal meteor to actually move the planet around. And frankly, we'd have bigger problems before the planet starts moving if that happened. So, momentum is always conserved, even if it doesn't look like it is. If you just hit a big enough object, it'll give the illusion of it vanishing. It just went into something too big to notice its motion. Questions? All right, that's it for today. Have a good weekend. Let me know if you need anything, including but not limited to test or current midterm score questions. Have a great day. Easy. Welcome.
Good day.
See you next. I had one, someone took it, which is upsetting because now I can't throw my markers at it and miss. Sorry. I know they exist around here. There's one in
Or
one of
in the
three if you need
bathrooms,
one.
probably.
That's fair.